as we're going to actually talk today about whole life fatigue inside of design life, and its focus is looking at weld fatigue. The agenda for today is to go off and look at whole life welds. We're going to start out with a brief introduction of fatigue life of welds, looking at approaches to do weld analysis. We'll then go in and focus in on the whole life methodology, how it actually works, and then how it's been integrated into design life's whole life for welds. We'll do a quick look at a correlation study between experimental and whole life predictions, and then finish up with questions. When we look at fatigue predictions of welds, they tend to be quite different than the fatigue predictions we make of the parent metal. And there's several reasons for that. One, the weld geometry has large stress concentrations, at times existing crack initiation sites, at things like the toe, the root. Many times there's very, very high tensile residual stresses left in the weld from the welding process. And then we've gone in and many times deposited weld metal. We've taken the parent metal and have transformed it into a heat-affected zone. So there's a lot of complexity in the welds. And we start looking at weld performance, we see that the performance of the welds in fatigue are substantially less than that of the parent metal. And you can see it from the graph we have here, where if I were to look at just a standard fatigue curve for an unnotched specimen, look at the curve for a specimen with a notch, and then when I look at the curve for the specimen that has been welded, even though the weld isn't carrying any load, it has substantially lower performance. And more importantly, at times it has changed the slope of the curve. All of a sudden we see now that the fatigue behavior of this welded part is going to look much more like crack growth than it is crack initiation. And we can see that by that steep slope of the fatigue curve. Something we see many times, again, is the fact that the fatigue performance of these unimproved welds really don't reflect the parent strength. So when we look at how we're going to analyze welds, we actually have several approaches we could look at. We'll start with the first one in the upper left-hand corner, crack growth. And as we see, the weld behavior is crack growth, but historically crack growth has not been used much for a couple reasons in terms of looking at a finite element-based fatigue solution. And one is that it's very point-wise oriented. You know, I literally have to go in and specify where the crack is going to be, what the crack looks like, what the crack size is, and the initial crack size basically drives the entire solution. So there's a lot of ambiguity there. And then it's expensive. And so historically, it's not been really built into finite element solutions. There's another approach, which we see as a local notch stress approach, and here we attempt to get as detailed a stress as we can out of the weld geometry. That might be from a very fine FE model, but again, if one does that type of detail at the weld, it's virtually impossible to mesh a real structure. Another approach is to go in and have some sort of breakout model where we have a coarse model feeding the breakout model either some sort of nominal stress or displacement or forces, and then it returns back a stress. One of the issues I've seen with that is I've never seen these breakout models be fully 3D. They tend to be cross sections of the weld, looking at the weld kind of in the center line, where most times these welds fail at weld ends. So I haven't seen that used that much. The third approach, and what the most generalized approach for welds, is something called structural stress. And here we take our model and we're looking for either on the actual model or the final model, we're looking for a stress that exists at the weld toe without the weld toe being there. It can be obtained in a variety of different ways, whether it's a nominal stress approach, a hotspot stress where I extrapolate up to the weld toe. It can be calculated from nodal forces and moments out of a final element model. It can be calculated as like through thickness stress profile that has been linearized. So there's a variety of ways to get this structural stress, and the real beauty of a structural stress is it tends to be independent of the meshing, such that I could use a coarse model, fine model, include the weld toe, not include the weld toe, and come back and have a structural stress that's repeatable. And then what we do is we take that structural stress and we use that and reverse engineer a fatigue curve from that using our final element models. And so what we end up with is a fatigue curve. We call it a component fatigue curve. It's no longer material behavior. It's not the weld metal. It's not the heat affected zone. It's a fatigue curve that describes the weld itself. It has baked into it not only the material properties, but residual stresses, stress risers. Everything is embodied in that fatigue curve. It makes this very, very powerful and useful in terms of going off and doing a wide applications of fatigue analyses. However, it's not perfect. When we use a structural stress approach, and what we're representing is basically the typical behavior of a weld. Again, we're looking at, like, all these welds act the same. It usually does not include any sort of improvements we've made into the weld geometry or the welding procedure. We're relying on the fact that the welding process has taken away, and specifically usually because of the geometry there, has taken away all the aspects or most of the aspects of the parent metal strength, that we can go in and use a structural stress approach and collapse all the weld data down to a single curve, or maybe a family of curves, depending on the approach you're using. The problem with that, as you can see, I have here weld data. This actually has to be spot weld, and it's a series of different test specimens, and it collapses quite well. Even though I have different size specimens, different types of loading, it collapses quite well until you look at it and notice that there still is a scatter band there that's more than a decade wide. I have down here basically variations in my welds. They're more than a factor of 20 difference. In order to use these types of calculations, what I need to do is I have to have my design curve below that scatter band. Now, the moment I do that, I'm going to be conservative for a large number of my welds. So in order for me to go off and do this, I can go in and be over-conservative and use this design curve across all my welds. And in many cases, that's what we do, because we don't really have control of the weld geometry per se. We're really modeling the geometry of the part, and those parts are going to be welded together. If we want to go in and be more precise, we need to go in and understand more about the weld and go off and use other approaches, hence crack growth. So when I start looking at specific welds, there's welds where I actually have a great deal of control on the design. If I look at the upper left-hand corner, here I have decisions I can make in how I'm going to bevel the parts prior to welding. I could go in and make decisions on how many passes I need to weld that, what the order of the passes are. I could go in after the fact and modify the weld, grind off weld toes, shot peen it. I could change a great deal about that weld to improve its performance. Same thing with the lower. If I go off and look at some of the details in the lower picture, again, when I look at that, I have control of how I'm going to design that weld. I'm designing the weld, not necessarily the geometry that's going to be welded. And this actually applies in more applications in these construction. As we start looking at lightweighting today, we see that we're starting to bring in vehicle structures that now incorporate things such as extrusions and castings. And we now end up with welds in those structures that actually are critical. I'm not looking at 2 or 3 meters of weld carrying the load. I'm looking at a relatively small section that's been welded, and that weld is a great deal of care has been taken in designing that weld. In these situations, we can be far more precise in analyzing those welds. So what we're going to look at is an approach we call WholeLife. And in essence, WholeLife is a unified approach to fatigue predictions. It incorporates both the initiation and crack growth as part of the analysis. It is a crack growth approach. It could be applied to a variety of fatigue predictions, but for our first release, we're going to target this at welds. And so this is going to be basically a weld analysis. We're going to see that we're going to put in more detail about the welds in terms of its geometry and residual stresses and information that will allow us to go off and be far more precise in our fatigue predictions, and such that it's going to give us much better accuracy in terms of our predictions than going off and just using a standard stress, structural stress approach. And again, this isn't applicable. This is not going to be the ideal solution for all welds, but in certain welds, especially the ones that are being engineered, this is going to be a much better solution than going off and trying to use a conventional methodology. What we've done is taken this approach and have built it into design life to use on a finite element model, basically piggybacking off of our standard seam weld capability. What WholeLife is actually a unified theory of fatigue that was developed by Professor Greg Glink out of Waterloo. It is looking at the entire life, fatigue life. So we're looking at both capturing initiation and propagation of the crack. What we're using inside of design life is the standard seam weld methodology. So it's using standard FE analysis driving our current structural stress approach for seam weld, and then using that information to pass down to a second analysis that will do critical locations in great detail using WholeLife. It'll give us the ability to go in and bring in more information about those welds in terms of geometry and residual stresses to go and do a far more precise prediction. The standard seam weld approach inside design life allows us to go off and look at multiple locations, multiple failure paths. And so we can bring those all in as a first pass, identify critical locations, and apply the WholeLife procedure to that. An important aspect is that we have created this WholeLife methodology that allows us to go in and use multi-axial loading. So I can use the standard loading I expect to see on my structure, dozens of load cases and load histories coming in, and we will basically turn those into structural stress histories that we'll use in the crack growth calculation. Again, not only are we looking at the actual operational loads coming in, but we're able to capture, if we know those, the residual stresses left in the welds and use those to improve the prediction. Okay, the whole life methodology that Professor Galinka has presented actually is a slight variation on what we normally look at as crack growth. What he envisions is the crack is actually a series of initiations through individual grains in the structure. And so each individual grain is a crack initiation site. It fails, starts to lengthen the crack. What he sees in this is that in a standard crack analysis, we assume that the crack tip comes to a very sharp point, and that basically that sharp point has an infinite stress concentration, a singularity. He sees this as we always have a finite radius at the crack tip. That radius, he calls it rho star, is on the order of the grain size in the material. What this gives us now is the ability to go in and do a detailed stress analysis and calculate what the actual stresses are at the crack tip, in front of the crack tip, and even behind the crack tip. It is crack growth, and we start out with a standard Harris curve, a curve that basically describes our crack growth behavior. And if we look at the crack growth curve, the vertical axis is this dAdn. In essence, what it means, if I have an individual load cycle, how much does the crack grow? dA is the crack growth, dn is the number of cycles. Down at the bottom, we have this driving force, this parameter. Historically, we'd have looked at that as being a stress intensity range. What we are looking at it here is this driving force parameter, and this driving force parameter is actually a combination of the stress intensities. So what he's done is to use Walker. For any of those people familiar with strain life, we use things like Smith-Watson-Topper for a strain life curve to account for mean stresses. This is the same sort of configuration where we have a stress intensity range, so that's going to be our cycle, and then we multiply it with a parameter that's a max stress intensity. This whole concept of Walker is that we actually give them exponents that are different than 0.5. But this allows us to go in and have a single definition that captures not only the crack growth, but also how the changes in R ratio will affect that. The stress intensities here are pretty standard stress intensities with a couple modifications. The big modifications, besides the stress intensity that's coming from the applied load being the sigma, so that's the stress away from the crack, we can also bring in a stress intensity that's a function of the residual stresses. Residual stresses being things like the residual stress profile left from the welding process, residual stresses left from the plasticity that occurs due to the crack growth operations. So they can be brought in as well to basically give us a better solution. And finally, there is one additional parameter here that is a correction factor when the crack is very, very small. One of the benefits of this approach, typically in a normal crack growth analysis, you're forced to specify a starting crack size, and the life is very, very sensitive to that initial assessment. Here, if we specify the crack size as this rho star, this initial parameter inside the crack growth equation, what we capture is the initiation as well as propagation. So we're not making a guess at what the initial size is. This is a parameter that has been reverse engineered from the data and allows us to go off and match initiation and add to that propagation, removing this issue of what do we use as a starting crack size. When we look at the stress intensity that we calculate, inside of WholeLife, we're using universal weight functions. And for us, what that really means is when one looks at how one gets a stress intensity factor, many times they come out of handbooks like Tata or in Paris and Irwin, where they'll have their very specified geometries of the crack shape, specified geometries of the part geometry the crack's going through, and then very simplified loading conditions. With the application of weight functions, we have a specified crack geometry, but then we have the ability to go in and have a much more complex part geometry and stress distribution applied to that. So the whole concept of universal weight function is it is a function I can apply to the stress distribution through my part without the crack being there that will give me the stress intensity factor I need for that crack. The big benefit is it gives us now the ability to have a much more widely applied stress intensity factor on our geometry. If we can go in and predict what the stress profiles are through the crack path for our uncracked part, we can use that to calculate the stress intensity factors directly. So just bear with me, it's just a bit of math, but what we actually start out with now is a crack that isn't a sharp discontinuity. It actually has a finite radius. And because we have this non-singular crack tip, we're actually able to go off and predict elastically what the stress profile would be when I applied, let's say, a tensile load basically parallel to that crack. And so we're able to go off and predict the stress profile directly because we know the radius of the crack tip, we know what we're applying as the far field stress. Now, the first thing we see is this profile here is elastic. And we can see that we've already exceeded yield. And so the second piece of this is going off, understanding what we've predicted elastically using Ramberg-Osgood. You're basically using just simple plasticity calculations in the Ramberg-Osgood equation and taking the, in essence, strain energy that was above yield and applying it as a new stress profile in front of our crack. So we're able to go in and predict what the stress profile is in tension in front of our crack tip. And now remembering just simple strain life calculations, whenever we have a tensile overload and we release the load, we end up basically producing a compressive residual stress. If we go off and look at this profile at various locations, we can go in and calculate what the stress tensile is, go through Ramberg-Osgood, and predict now a compressive residual stress left over from the unloading process. And so we're actually able to go in and, through the unloading process, go in and predict this compressive region in front of the crack tip. That compressive region is what's going to cause retardation of the crack growth. So we now have a detailed stress that the crack has to grow through. We also have the ability to actually grow that crack through this residual stress and capture what the stress state is behind the crack tip as well. And those detailed stresses are used in the crack closure calculation. So the key here to using this blunt notch tip is the fact that we can go off and do relatively simple plasticity calculations and come up with a very accurate prediction of what the stress state is ahead of the crack and behind the crack tip, and use those to basically control the crack growth rate. So we have that as a basic technology, and what we've done is taken that and put it into the weld calculation that we use inside of Design Life. We call that WholeLife Welds. In terms of inputs for that, as I had said, we start out with a seam weld analysis inside of Design Life, and so there we're going to have the standard inputs. We're going to have a finite element model. In this case, it's relatively coarse. It doesn't have to capture all the detailed stresses. It's used to calculate structural stresses. And we have various load cases on this, and those load cases are paired up with time histories. And so this would allow us to go in, run through, and calculate stress histories, structural stress histories, anywhere in that model, and we've specified locations using the seam weld approach, that places we want to go off and do calculations for crack growth of the welds. Second piece of this now, once we've gone off and run the standard seam weld and we've identified locations we want to see in more detail, we bring in information about those locations. That information is going to allow us to go in and calculate the stress intensity factors that we need for those locations. Using the weight functions, what that information actually is are through thickness profiles. So we're going to actually go off and look at our crack path and put in that crack path what the stress state is. And the way that we're actually doing inside Design Life, we're actually bringing in two stress states. One stress state due to a pure axial loading, one stress state due to a pure bending load. We can get those a couple different ways. So what we're bringing in is a KT stress, a stress concentration factor stress that we're going to apply to our structural stresses. And so we take this KT, apply it to our structural stress, and what we actually have is a true stress profile. And we're going to bring those in as a profile through the thickness, and again, one for pure bending, one for pure membrane. And we can get those either from empirical equations, and we have one built into Design Life, WholeLife Welds today that uses Monahan to look at this fillet weld, specify parameters in terms of thickness of the plate, radius of the toe, the angle of the weld bead, and it can calculate these profiles for us. There's also a methodology to bring in tables that would be depth versus these profiles, and these profiles can be calculated from detailed breakout models of the geometry. So a very small model of the weld itself, and get the profiles from that. Either way, we bring these profiles in along with a possible residual stress profile. Residual stresses could be measured. There's a variety of experimental techniques to get these. They also could be simulated via CAE, modeling the welding process. But those can be brought in to describe the weld. And then finally, we have material properties. And the actual properties we need to drive this are twofold. We're showing strain life here, but realistically, we're not using the damage curve for strain life at all. We're using the stress strain curve, the Ramberg-Osgood representation, so we can go off and do the plasticity. And then we also need to have a set of crack growth curves, at least two curves at different R ratios. And we're going to take those curves and we're going to collapse them down to that single Walker curve that you saw. And again, this is part of the process that's going to give us this one crack growth damage curve, the row start, the initial crack size that we're going to use that is basically defines initiation. And that is the information we need to go off and do the predictions. What I'm going to do is look at how this actually works, and to start out with, we'll talk about a correlation study. This has been piggybacked off of a SAE committee, the Fatigue Design Evaluation Committee, and it's a project they've been working on for 5 or 6 years. It's called the Total Life Project. And the start of the project was to go off and to come up with an improved fatigue prediction approach for fatigue performance of welds, and they were specifically looking at things like ground vehicle. And to do this, they've actually been very methodical. They have selected material specimens that were going to be very difficult to analyze in terms of crack growth. This happens to be an A36 steel, which tends to be very ductile, and so it's a hard material to predict crack growth through. They have developed welded specimens from this material, and as a control, they've actually taken the shape of the welded specimens and machined them out of blocks of the whole material to have as a control. So they have the geometry there without any of the welding process. And they've set this up, done extensive evaluations of the welding process, evaluations of residual stresses, put together a test plan where they've brought in a variety of different loading conditions to try to look at different areas of basically of fatigue growth. So some of these loads are constant amplitude, some are block histories where we have underloads coming in, full random time histories, and they've set up a whole sequence of physical tests, and we're only going to look at the welded ones today. But they've gone off and tested these specimens to failure. Failure in this case tends to be a significant load drop-off. This is a very ductile material, so at some point the crack gets large enough, the loads just drop off, and that's considered to be the full failure. And they have done this for all these different loading conditions on these specific specimens. We've taken this information and brought in what we need in terms of inputs, and that is the initial locations where we're going to look at failure. We've brought in the stress profiles, and these actually the stress profile we're interested in here is the black dots. This is actually the stress profile through the welded specimen, and this was calculated via final element model. So it was a very detailed final element model through the cross-section of the toe that's going to fail. And these are measurements off of that FE model. We also brought in one of the residual stress profiles that was experimentally calculated, and we brought in detailed material properties that the Fatigue Design and Evaluation Committee calculated on this A36. So they actually had both strain life data to give us the Ramberg-Osgood coefficients as well as crack growth data. And that was brought into the implementation of WholeLife Welds. And so I have as an input a relatively coarse model of that test specimen and loaded the way, basically fixtured and loaded as it was in the test. It comes into the WholeLife glyph, and the WholeLife glyph contains both a seam weld solver as well as a WholeLife solver. And the seam weld solver is given multiple locations. In this case, we had basically locations on both faces of the toe. So we looked at both the front and back face along the toe and along its width, and had multiple locations specified for the seam weld analysis. The first seam weld analysis was done to find critical locations, and you can specify how many and how they're distributed, but we just asked for one location to be grabbed, the worst location in the model. We bring in the actual loading on the part, and so this was a series of either constant amplitude, the block history, or in this case you're looking at the variable amplitude loading, and we did a WholeLife analysis on the critical location for each of those different loading conditions. And one of the things you get out of WholeLife is a very detailed description of the crack growth through the part. And so the output of this was set up as a report. And so we're getting out of the WholeLife calculation things such as the growth over the number of cycles. And the type of crack that we're using in WholeLife, actually it's come down here for a second, is the semi-elliptical crack. This crack actually allows you to have a varying aspect ratio over time. So it could start out as a semicircle and eventually grow into ellipse depending on what the stress state it is growing through. And so what comes out of this is a history of the red history here is basically the length of the crack over a number of cycles. The red is into the part. The blue history is the width. It's how wide the crack is growing on the face. And the lower left-hand plot here are 4 snapshots of the crack geometry at different points in life. So we're able to go off and basically map out what the crack looks like and come back in and basically specify a variety of termination conditions. They could either be a max crack length, they could be fast fracture is approaching because we're exceeding the notch toughness. They could be number of cycles, and so it will go off, run till it hits one of these termination conditions, and then give us the results. And from this, we went off, tested all the welded specimens that they had done, and what we've done is plot here a correlation graph. This graph, if you look at the horizontal axis, is the life actually predicted by the experiment. So this is the test life. So every one of those tests ran to a certain life, and so the horizontal axis is the test. The vertical axis is the whole life prediction. It is the analytical prediction of life. So if the prediction matched the experimental test exactly, the answers would be on this black line, this diagonal line, where the two have exactly the same value. The red line is a factor of 2 on life off of that exact answer in the unconservative solution. In this case, the fatigue prediction in whole life was larger than the test. And then the green line is a factor 2 off in the conservative, hence that the fatigue prediction specified a lower life. And you'll see that all these blue squares are the actual welded specimens from the FAA tests. And we fit within that basically a factor 2 scatter band with that. To go off and highlight the differences between a structural stress approach and this whole life approach, we've gone in and reanalyzed those tests using just a standard seam weld approach. So this is a solid model seam weld analysis using the standard seam steel that's in the nCode database, and the light blue stars are the predictions from the seam weld analysis. And you look at, oh, look at, they're off the band. But again, remember, the whole purpose of the structural stress approach was to go in without a great deal of knowledge and to describe the performance, the design performance of those welds. So we're going in and we have a single weld curve that describes all these steel welds. And we use this one-size-fits-all to come up and talk about a design curve we can use for these welds when we don't know a great deal about those welds. And hence, you'll see that our predictions are over-conservative, but again, they're supposed to be conservative because there is a fair scatter band in this set of data. The key here is this is an ideal approach when I'm doing high-volume welds and I really can't tell you what the weld's going to look like. But if we know more about the weld, we can go in and put that information into our analysis and get better predictions. And that's really what we're looking at here in terms of whole life. In whole life, we're bringing in the actual weld geometry in terms of these stress profiles that we have either predicted via analytical solutions or numeric solutions. We can bring in a residual stress profile due to the welding process. And then we bring in crack growth properties as well, and this allows us to go off and do these calculations without the excessive conservatism we need for the structural stresses. As a benefit, on a structural stress approach, you're looking at a fatigue curve, and that fatigue curve represents some definition of failure. That may have been the part goes up, basically breaks in two. That may have been a drop-off in displacement or load. It may have been a visible crack. But whoever did those tests came up with a criteria that said the part failed. In whole life, we can say what the failure criteria is because we're putting those conditions in terms of fast fracture, in terms of crack size, so we can go in and control that. Another major benefit at times, cracks will start at a location where we have a high stress riser, but as they grow out of that stress field, they stop. They basically just stagnate. Using WholeLife, we can actually predict that. We can go off and see cracks start to initiate, but then basically stop after they've walked out of the stress riser. And again, we have already shown that the fact we can go in and correlate to these actual test specimens with a pretty high degree of accuracy. A factor of 2 is actually a very good prediction for a fatigue calculation. In most cases, we get within a factor of 5 to 10, we feel really proud of ourselves. Okay, so in terms of WholeLife Weld, what we're looking at here is the integration of crack growth into a fatigue, basically a CA-based, final base fatigue solution, in this case for welds. In the actual model, we're going in and calculating the structural stresses and doing this calculation. We can have a fairly coarse model, either in terms of solids, and in the first release, we're supporting the solid seam weld as our input. At the July release, we'll have shells out there as well. So we can actually do this in a shell model as well in terms of doing the crack growth in WholeLife. The user defines locations that he brings into the seam weld analysis, and that's either a series of solid seam weld locations we want to do the calculation on, or in a shell model, it would be a set of shells that represent the welds. And the WholeLife solver goes in, solves those, uses the results from seam weld to automatically filter down to critical locations. And those critical locations are now reanalyzed in WholeLife. One of the key aspects here is that we are going in and allowing you to bring in real loading. Problem with crack growth many times is the fact that we're using standard stress intensity factors, so we're really limited to very simplified stress states, loading, so we can bring in. Using the weight functions, its ability to have complex stresses, and then the way we've actually integrated the calculations inside of WholeLife Weld, we can go in and deal with multi-axial loading coming in and still have an efficient solution in terms of the well-produced fatigue life. We've basically taken crack growth and seamlessly have integrated it into a final solution. In fact, just to kind of highlighting this, what we have on this plot is a cruciform model where basically the load goes through the vertical member. The welds are the load-carrying part, taking the load through the vertical member, across the horizontal member, and back out. And what we've done there is specify locations at multiple positions, along the toes and roots of all those welds, through the throat at multiple angles for all those welds. Seam weld has gone off, picked critical locations based on the seam weld analysis, and those locations were analyzed in WholeLife to go off and give us the predictions. Okay, well, in summary, and hopefully I talked about this, is that what WholeLife is actually a unified approach to fatigue. It's basically a combination of initiation followed by propagation. Even though it's applicable to all fatigue analyses, we are focused on this release, and actually part of the next release, at applying this on welds. So it's going to be WholeLife Welds. It gives us a much higher accuracy, precision and accuracy over a structural stress approach. It's really geared towards welds where we're engineering the weld. And so here we say it's well suited to light weighting, to thick welds. Realistically, what we're looking at are welds where I know more about the weld. If I know enough about the weld in terms of geometry, possibly residual stresses, I can bring that information in and get much better answers. And again, we're showing high correlation in terms of the test data we have, not only in life, but actually in terms of the predicted weld profile against the actual profile of the test specimens.